environmental accretion. Here, I don't need to do an introduction to what Sagittarius A star is. I guess we all agree that it's big as a black hole in our sky. It's close enough that we can see the event horizon. It's close enough that we can explore its environment in the most fine details. And that's the only black hole through which we can possibly access such fine details. It's also ideal candidate to explore new horizon phenomena, test beyond general relativity theories. It's an ideal candidate from the point of view of astrophysics to study mechanics of the black hole accretion, feedback, feeding, etc. Essentially the forces shaping the universe itself through the cosmic times. I asked Fabio about whether the little introductory materials would be appreciated or sound offensive. And Fabio said they should be definitely appreciated. So I'll do a very short introduction for those who actually not working in astrophysics or black hole accretion. So there are two distinct types of environments black holes live in, and they're depicted here. One of them is a thin disk accretion, the other one is a thick disk accretion. For the thin disk accretion, what you need is you need the abundance of material around the black hole. In this case, your cooling will be efficient, and the mechanics will go like this. Your parcels of the gas will interact with each other, they lose orbital momentum, they fall toward the black hole, they get heated up because of this conversion of the potential energy to kinetic energy. Then everything interacts happily, it radiates, we see the get rid of this excess temperature and settles in the thin disk. Example with thin disks is the most common example of the black hole accretion you can find on the internet. So those are the first one which shows up. And in principle, also that's clearly not black hole accretion. This is also a thin disk accretion. Saturn rings accretion disk, thin accretion disk. But what would happen if the gas cannot efficiently cool? In this case, your parcels of gas again interact, they fall, lose orbital momentum, they fall close to the black hole, they're heating up. But if there is no abundance of material around, they would like to interact and get rid of this excessive temperature. But your electrons, which are mostly primarily responsible for radiation because they are light particles, and your protons, which are heavy particles, and those who mostly get most of the thermal energy from pulling potential well, they just don't meet each other very often. And because of that, they don't have enough time to pass, they equilibrate, radiate, and this excess of the temperature is not radiated away and the disk stays thick. Something of the picture you have here. Yeah, this is just a summary of what I just said. What do we know about the accretion of our own galactic center black hole? Observationally, we know that at about 10 to the 5 Schwarzschild radii, accretion rate by 3 10 to the minus 6 solar masses a year. How do we know this? We know this is from X-ray observations. This is the Chandra observation of the galactic center. From this observation, we can figure out the temperatures and the densities of the material, and then find in which exactly place we have such a condition that thermal energy of particles no longer enough to escape the gravity of the black hole. That's going to be your body radius and the stuff inside bound to fall in. Why does only give us information about 10 to the 5 Schwarzschild radii? It's because of this. So this is a little dotted circle is 10 to the 5 Schwarzschild radii, 1 arcsecond. And it's matching Chandra's resolution. So you can't get any information which is the scale smaller than this from X-ray observations. We also know from observations from that accretion rate at few Schwarzschild radii is something around 10 to the minus 7, 10 to the minus 8 solar masses a year. This we know from polarization measurements. But what happens in between in this case? So we need to figure out whether this is abundance or opposite of abundance of material around the black hole. So we look at those numbers, and the good measure of how abundant and how much accretion is there is Eddington accretion rate. You'll get Eddington when your materials pull in, radiate, and its radiation pushes away the particles, preventing them falling into the black hole. So Eddington accretion rate for a black hole the size Sagittarius A star is 10 to the -1 solar mass a year, which is much, much, much larger than any of those numbers below. So we clearly can say that this is definitely not a thin disk because the amount of stuff is not abundant. And it must be something like this. It's a depiction of a thick disk, not to scale. In this case, it's going to be a thick disk, or kind of side views going to be something like this, cross section on the side. This sort of system been studied for a long time and been fairly well understood. But when we talk about exactly our own galactic center black hole, what becomes really important is exactly how much of outflow we have, what sort of magnetic field we have there, what sort of, how strong is the convection. In those cases, depends on what your favorite conditions are. There is a wide range of model, which you can say should be reasonably described as a star. And technically, practically, we're in a condition that we know how much accretion goes at the pure fraction radii. We know how much is going at 10 to the 5. What happens in between? We're heavily relying on simulations, and depends on your favorite model. For example, density can scale anywhere between the radius in -3/2 to radius in -1/2. This might not sound scary difference, but to give you like more visual example, if you're looking at two radii, one of them 100 times bigger than the other, and you ask the question how fast the density falls, is it one of those power law will give you that the density at the further part is 10 times less, the other one will give you the 1,000 times less. So it's quite a big difference if you look at this. Simulations, the most common approach to the simulating accretion on the black hole, and Sagittarius A star as well, is to set up the torus at large radii, which will feed the accretion into the black hole itself. And this is just one of the examples of the initial conditions. So you have a big torus, you set up the density in the equatorial plane, magnetic flux in the equatorial plane, and you set your simulations right. So the question I want to ask is that we all agreed, as I said earlier, that the Sagittarius A star, the Sagittarius A star at the center of our galaxy, is the one which gives us a clue to many physical questions about black hole physics. So how far, and we heavily rely on simulations to fill the gaps between observational data, how far can we go in ignoring the environment of the black hole? More precisely, how far we shouldn't be going to get the environment of that black hole. So where is the boundary lies when we still study the Sagittarius A star, the one at the center of our galaxy, or some similar black hole with similar conditions. So the black hole environment and extending black hole physics to more extended scales and to produce more realistic simulations of the inner few parsecs of the galactic center of the black hole is going to be the topic of my talk. So for me, the story began somewhere around 2019, yes, when I was interested in the contribution of the cooler gases to the accretion to the black hole. So of course, we all agree that we do not expect gases, we only expect very hot gas into the 7 and higher, very close to the black hole. But how far we should still expect some cooler gases as well, because the galactic center is filled with gases at various temperatures, complicated multi-phase structure. So I was looking at the cool gases in the innermost accretion region of a black hole. In this case, I will define it approximately as a Poynter radius. And I saw this. This is the cool disk seen in recombination line of hydrogen. It's resolved. You see rotation. You can see which direction it's rotating. You can see it's a disk. You can see there is a hole in the middle. You know that the temperature is about 10 to the 4 Kelvin. And this sort of cool gases, which is not X-ray, this is not X-ray emitting. This is much cooler than that, much cooler than that. I will not expect it to be present in this region. By the way, I'm happy for you to interrupt me anytime and ask questions. It's very harder to figure out which slide you're asking. It's going to be 10 slides. So yes, and this disk series well within Poynter radius, about 10 to the within 10 to the 4 Schwarzschild radii, within a kind of semi-resolved. You can't see the fine structures. Here is the property of the disk, of that disk. And I also want to, it has the mass of about 10 to the minus 5 solar masses. It is either inclined to this line of sight of sub-Keplerian. It's hard to say. It's more recently, I also showed that it contains the neutral gas fraction as well, and some sizable neutral gas fraction. It's smaller, but about 4 times, but still comparable to this, to the mass of the ionized gas fraction. And this wonderful student at Princeton University, Tianshu Wang, who worked with me on this neutral gas fraction. Yes, please.
So this high velocity cool gas,
yes,
is it spatially resolved in your map?
It is resolved to that point. So you see blue shift if you see red shift.
And
but
they are separate? So,
yeah, you see them separate.
okay, so you can actually tell which way the disk is
Yeah.
going.
So this is blue shift coming to, I'll show it in the context of the 2 parsecs of the galactic center.
Right.
So this side comes toward us and then it goes.
So the axis is like this, rotation axis.
Yes.
This is what it's doing.
It's similar. I will show it like 20 some slide further. It's a similar direction as the plane of the galaxy in most of the cool structures, which lives on the 2 parsecs of the galactic center.
Great.
But you'll see it.
That's
there.
a future slide. Okay.
I redid this talk 2 days ago.
It's all right. We
And
will
you're right,
interrupt
it's
you
a
and then
good
you can
point.
tell us. Yeah.
I might have put it, next time I won't do this. And I just wanted to put an accretion rate in the context. So again, 10 to the minus 6 here, 10 to the minus 7, minus 8 there. And the cool fraction accretion is 3 10 to the minus 7, which is in between, just a reasonable estimate. And because we have, we can expect the hot fraction accretion of the of similar order.
How do you know it's m dot? All you're seeing is some gas.
Yeah, it's agreed. It's model dependent. So your model is that it's a violent environment. You don't expect anything being super smooth there. So it's a bunch of clumps. So clumps collide with each other, lose orbital momentum, as you just should calculate probability of the clumps to collide and rain on the black hole. Yes, it's an order of magnitude. Yes, and you can constrain approximately the properties of this clump from different observations. So you set them. Originally you set them, and you have a next observation, which gives you another clues, and you just keep adjusting this till you get to the point. Hopefully, once you know everything about the structure.
But they're very small clumps, right?
Yeah.
With a high covering fraction.
Depends how high covering you want, how high you high.
As in, it's nearly a disk.
It's very holy disk. It's a covering fraction. I think something of order 5%.
Oh, okay.
So it's a dense clumps. It's a very small amount of material. It's just spread around. It has fairly high density, so there are big holes between them, but you not resolving the holes.
And
So
that
the covering
is
fraction.
okay, that's consistent with the velocity measurement, in the sense that
Your inclination can give you velocity measurements. So I cannot constrain a inclination. I can neither say it's if it is inclination or subject related to direction, something. I can't say that, so it's somewhere there. I can, if you're interested in that, I can tell you where the 5% is coming from.
We can do it all.
Yeah. Okay, so
Can I ask a question?
so the
I
data
think
can,
Shep has a question.
oh sorry, I can't.
Yeah, maybe you're going to touch on this later, but what is the relationship between the sense of rotation of that disk and the S2 star, for example, or the other stars? Is there any correlation?
Really, I should have the slides.
Yeah, that's a future slide.
It's called-
Oh.
Yeah, I'm sorry about that.
Animation.
No, it's not related to the, I don't know if you see me.
No.
No, okay, fine.
No, I see you. Yeah.
He'll be patient, yeah. We'll
Okay,
wait.
I'll be patient. Right now, I'm seeing
So,
people's feet.
No, the point is S2 stars has nothing, it doesn't have to align with it, and it doesn't seem to be aligning. I think the rotation is different direction from the S2 star by my memory. It's also have a angle. So they are not, so yeah, they're not coincidence. There's tons of stars there, you know, they're all total mess there. And the dominant source, I'll also talk about this later. The dominant source of accretion material is not S2 star.
Okay, thanks.
This little bragging point, all this data come from the ALMA observation, and although I theorist, you know, if you want to get things done, sometimes you have to do it yourself. So sub-millimeter recombination, it's observed in sub-millimeter recombination line of hydrogen, transition from 31 to 30, which puts it in sub-millimeter range.
Is that you?
Yes.
It's allowed, no?
It's hard, yeah. I have a
Are you
video.
allowed to do that?
I'm not sure there's no one there.
You can't do it, okay.
There's no one there.
I won't put this on YouTube, don't worry.
It's okay. I have a video of this. Someone asked me how did you get there. I said, I have a video. So yeah, it's Lena visiting Alma High side. So yes, that consists of a series of successful and top-rated ALMA proposals over the course of about 6 years. Most of the observational stuff which I'm talking about is coming from here. And yeah, you see the picture of the PI we already discussed. All right, has this disk been seen in the simulations? Let me answer this question first by stating what sort of simulations I'm talking about. I'm talking here about the simulations without cost. Realistic simulations is the simulations which attempt to model the galactic center to some degrees. So there are two groups which work on realistic simulations of the galactic center with aim to reproduce Chandra's observations. So the setup is the following: you have 15 Wolf-Rayet stars shading winds. These winds fill the volume, and after some time, when it's all more settles down, you can look and see what sort of fake Chandra observations you'll get and how it will look. This is from Sean Ressler's simulations, and this is observations of Chandra. There is a fair amount of similarity here. So the simulations of that sort reproduce Chandra's observations fairly well. So the answer to the question whether the disk been seen after my paper, this paper came out by Chilean and German group by Calderon et al. 2020. They reported they have similar simulations, and here I keep all the panels, so you see this bunch of Wolf-Rayet stars, how they start shading winds, and then how they fill all the volume and stuff will settle down. So when they run the simulation for extended period of time, for 3,000 years in this case, as they claim, they saw a structure forming close to the black hole. And So those panels are two scales of each other. And wait, this is even better. The white one here and the white one there is the same size. So you see the disk of bigger size. Orientation wasn't clear to me from the context of the paper. But they do see this thing forming, and also units are different. It's still 10 to the 5 short radii in both cases. This simulation also include interaction with IRS-13, which is another group of stars. So included pin claims about intermediate amount black hole, etc. And they say this interaction is quite important for collisions of brains. But the other group doesn't see this. It's again simulations to scale. Let me overlay the scales again. That's the same sizes. And as you can see, I'm not sure you can actually, the temperatures go from 10 to the 7 to almost 10 to the 9. So there's no cold fraction there at all. But there is also no IRS-13, so how you compare?
But shouldn't this gas be X-ray emitting? No, if it's 10 to the 7. Okay.
Yeah. That's why I showed you that.
I see, and so it's consistent with the.
That's the same simulations.
Oh, okay.
It's the same simulation for X-ray emission, and this is zoom in. Sorry, not this one, and it's a zoom in of the inner region, which tells you the range of temperatures. Yes.
This is interesting comparison.
Yeah.
As I recall, the Ressler simulations do not include radiative cooling.
Not yet.
Yeah,
Wait.
of what you are showing.
Wait.
Yeah,
They
but
do.
did these guys include cooling? Calderon?
They do, and Ressler simulation includes cooling, but not very far. They also included cooling. More recent simulations did, but that's going to be the subject of my second slide.
Okay.
I don't know how it's
all
going.
right. I can wait. I can wait. Yeah.
No, the
Yeah.
point is, so my next slide would be also this simulation segregator showing you reproducing Chandra to very close degrees. The question is, how well do they actually describe the black hole environment, and whether we can do better than this. To do this, and to give you a picture of the black hole environment, I'm going to put this picture here, and I'm going to build you galactic center, 2 parsecs around the galactic center. That's this image, structure by structure. So you get the view of how it's actually get a feel of what it is. Okay, I'll remove the Chandra image so it's not crowded. Things switched east and west due to astronomical convention. So first thing is there is the black hole itself. Second thing there, so the black hole has a mass of 4 × 10⁶ solar masses. So it's surrounded within about 1 parsec by a nuclear star cluster of a mass about 10⁶ solar masses. This is the plane of the galaxy. We see the line just because we are in the plane of the galaxy. I have rotational markers. The dot here says that it goes here, follow these arrows, and goes away on that side of the screen, away from us, where the cross is. This one is a mini spiral. It's 3 arms of the gas with temperatures between 10⁴ and 10⁵. Depends on where you are. So one arm goes away into the screen, goes behind, comes here. The other arm goes away up there, comes behind, comes here. This one we don't know because it doesn't have much of the rotation into the plane of the screen. This is circumnuclear disk. Carries about several 10⁴ solar masses. Of this, in my nomenclature, cold-ish gas with temperature between few Kelvin to about 500 Kelvin. It's a big disk, and it's also wide. It goes away into the screen up there, goes behind the black hole, comes here, and this part is in front of you. And now, this is the clockwise stellar system. The system contains most of those Wolf-Rayet stars we've been talking about. It's about 4 arc seconds. This is a remnant of an old jet. This is a pointy radius. There is a little dotted circle and the zoom in of this dotted circle. This is a famous S cluster, featuring about the same pointy radius as well, about the same size as the pointy radius, where most of those stars which are passing close live. This one is S2 star or SO2 star, it depends who you like more, UCLA or German group. You can see where my priorities lie. So it goes like this, it goes, I'm a black hole. It goes behind me, comes forward and do this. So this is a cool disk. And that, because I can't tell you which side, I can't put an arrow, but I can say that this side goes away and this way the side comes forward. You can also see that it's in agreement with the rotation of the galaxy, mini spiral arms, and the circumnuclear disk. That side goes away.
So this is what you're inferring from the ALMA data.
Yeah.
Okay.
Yeah.
Yeah,
And to give you an idea how complex this region is,
Can I ask a quick question?
all this plot is to scale. It's not to scale in terms of width of those lines, but it's to scale in terms of the size of this line. So that's a red arrow is the distance from the sun to the nearest star. So within the distance between sun and nearest star, we have 10 to the 6 stars, cluster, and all these big structures. So it's very dense and complex region. And that's overlay back to the Chandra image. So when we reproduce the Chandra image, all the structures are not somewhere far away, floating around. They are right there in this image. You just don't see them in the X-ray vision. You can actually see, if I remove the jet, you can see the trace of the jet. And the stars, which are shaded wings here, they come in right through those pieces of the mini spiral, and they're fairly close to this thing extends fairly deeply. All right, but so far, our simulations, the most realistic simulations of the galactic center look like that, which is a bit of far cry from this. So we decided a far cry from this, sorry about this direction. So we decided to make an improvement with Sean, and the most important contributor to this work is Stefan Solanke, who is the hopefully soon will be freshly minted graduate student. Doesn't have a graduate position yet, but we hope. Hoping because he's absolutely amazing. So, so we want to make Galactic Center look from this into this. And again, I'll make the structures in gray, those we don't include. So the structures in color are those we include. The structures in color and in boxes are those we include for the first time. This plot includes the structures we put as initial condition, as well as those which emerge naturally. And let me show you a bit of preview from the simulations. So this one is mid-plane density, mid-plane of the circumnuclear disk. So you can see that it's just introduced. So the wings start, and it's a zoom. So you are seeing everything. Now you see zooming into the center, now more to the center and more to the center. Zoom goes down, zooming closer to the center, and time runs horizontally. So you just introduce it, it starts interacting with wings and interacts more and more and more. We see a lot of this interesting interaction in the center because the wings are tearing pieces. And you're only seeing the slice here. So pieces which are torn to the side, they kind of leaving the image. That's how we explain in the mini spiral, because it depends on the size of the piece torn. If you tear a piece which is kind of small, this is just a cloud drop experiment. So you drop a cloud. If it's the piece you tore from the circumnuclear disk, it's small, it starts falling, it's get shredded and blown away with the winds.
And is the black
Yes.
hole basically a single particle?
Yeah.
Oh, okay, and then
Not
it-
a particle, there's some radius.
okay, and then but is it kept fixed or do you allow it to drift?
No, sitting there. Then if the cloud is too big, it doesn't for sure form you any arms. It just forms a big accretion disk. And there is a sweet spot here around 50-ish, 100-ish, where it makes you the big arms. And magically enough, that's exactly the mass of the big spiral. If you get 3 arms of that mass, you can just from there, from the stellar wind show that the mass of the big spiral will be around or 200 solar masses. 3 arms of the big spiral. This is a temperature plot, and this time it's not in the plane of the thingy, this torus, it's in the plane of the sky. And why I'm showing you this is I want to show you that. That's the temperatures here around 10 to the 6, oh, sorry, 10 to the 4 Kelvin, and you see little disk forming here. Oops. If you want to see it better, here it is. So that's a little disk forming there, consisting of 10 to the 4-ish Kelvin gas. So yes, the paper, we're currently writing it. So we, for the first time, we included the biggest gaseous players in the 2 parsecs around the galactic central black hole. This time, we track cooling up to 100 kelvins. Cooling was extended by a lot thanks to CFAN.
But assuming optically thin cooling or with radiative transfer?
Radiative transfer. No, you don't think so?
I don't think you have the code for that.
Isn't DREAMS Athena++?
Maybe, yeah.
But those simulations are Athena++.
Okay. So it includes the cooling.
Yes. So we see that the accretion structure is getting modified because the structures we actually observed in the observations appear in the simulations as well. And you know, stay tuned. We are writing because I've shown you already the plots in the chat from the paper. And I know I have not too much time, so I'm going to speak for a little bit about the part which I kind of wrapped under the rug, because we want to show a big picture. I would try to hide these little small details. And the small little details here is data analysis. And I want to talk about data analysis of the this cool disk observations. And to say a few words about this, I'd like to show you thing which seems a bit unrelated. I want to show you some negative relativities to the data say star. That's a structure function, which is in this case defined that you have light curves, flux with the time. You take your tau, time difference, you put it in your light curve and see flux here, subtract, square, drag it all across your light curve, and then average, take a square. And that's what is plotted. And this is a thing published in my paper with Günther Witzel in 21. And that was inspired by my interest sometimes in this bright near-infrared flares and the origin of like bright flares. But the point is, this thing looks like this, and those colorful stars on top is the structure function computed in the literature previously, which I took from the literature. This one is also, it's not that important, it's corrected for observational uncertainties. I can put these lines here and you'll see a factor of 100 on each scale of improvement. And this is nothing but a byproduct of the data analysis which is done for the cool disk detection in the galactic center. Because what is done for the cool disk is, I showed you the spec, and the spectrum, to free Miller-Jansky spectra. It's easy to detect free Miller-Jansky assignment. What's difficult to detect free Miller-Jansky broad line on top of 4 Jansky continuum. So to get the spectrum, what I need to do is to feed the continuum and subtract. So the only thing which was done here, instead of throwing away the subtract continuum, it's been actually output. And that's a very complex experiment. So you can't just point over there and do standard data analysis, which comes with your data reduction, and say here is the detection. There is lots and lots of work. And I was debating whether I should show you some preview group, and I decided that not at the moment, maybe in private. Also, constructing the structure function enable us to do some interesting science in terms of comparison in the various models with the observations. And I can say that we can. This one, I can extend it using historical data. We can reproduce this variability from bottom to the top. And let me go to my conclusions on big picture. My conclusions will be a look ahead, and conclusion will be split in 3 slides. The first one will be about observations. So the very existence of this cool disk in the middle of the Bondi radius is very helpful in a sense, because the cool disk itself can be used as a probe of the physics, because it's immersed in the hot accretion flow. And when we know the structures of the disk and the sort of interactions it's going through, we'll be able to figure out what sort of forces are acting in it. We'll be able to figure out, knowing the density of the clumps, we'll know the density outside of those clumps as well, because they're supposed to be in equilibrium to survive them. Also, the fact that this thing is there, cool gas can be imaged with much higher resolution than X-rays. X-rays are terribly difficult to focus, and this we can focus quite successfully. And the goal of the study, and there's lots of this IVA project, would be to constrain all the properties of the structure, see to figure out, does it feel the outflows? Because I want to point out also, we assume the outflows are there. We haven't seen them. We haven't seen any signature of currently existing outflow from the black hole. See the outflow, whether we see a jet, whether we see some direction, what sort of magnetic field is there. This allows us to probe almost anything we want. The simulation of look ahead is that we want to create the most realistic simulations of the inner 2 parsecs of the galactic center. These realistic simulations we're going to compare with the rest of them, and see how well we reproduce various properties, not just the structures which are living there, but also variability, short-term variability. And I already told you that our simulation seemed to be quite well on the way to reproduce the variability as we observe it. And also, yes, with our simulations, we show the emergence of the mini spiral, and the cool disk is less important because it's really hard to avoid creating that. And the biggest picture we have is that apart from Sagittarius A star nearby, we also have a M87, as everybody knows. And M87 star is very similar in size, but very different from the rest of the properties. So all of the methods which we apply to study Sagittarius star can also be used to study M87, apart from the fact that you can see Sagittarius at various points and see things moving there. And so the biggest goal of everything would be to create a model of interaction of low luminosity AGN with its environment. And most of the galaxies larger than Large Magellanic Cloud hosted underfed low luminosity black hole for most of their life. And this is really knowing the interaction of such black hole with the galaxy they live in. will really allow us to vastly improve cosmological simulations and understanding the universe. And with this, it's almost 45 minutes is what I'm aiming for. And thank you very much for your attention. I'm looking forward to your questions.
Thank you, Lena. Priya.
Fantastic work, really, really nice, because this is the piece that we are all missing when we go out to larger scales. And we are trying to model either with simple analytic models in galaxy formation, but this is the kind of detail we're missing. So I have two questions. First, how stable is this disk? All these structures that you're finding, how stable are they? How long have you evolved them in the simulations to see if they're stable?
The disk we see in the simulation so far a bit bigger than the one we see in observations. And the bigger the thing is, the more stable it is. There is also no S cluster there, so it's no stars which we could see in pieces of it.
Oh, because you're not including the nuclear star cluster.
We're not yet, not even S cluster itself, even like a bunch of near stars. We do step by step. So the structure there, as soon as it forms, it's really hard to keep it out of that. And it's fairly big, as you can see in both of those simulations. It's about not exactly 100 times bigger, but about the same in terms of the mass. It's more extended in the scales, several times in each direction. How stable the observed thing? The observed thing being seen for at least for epochs. It changes fair amount in the sense that you have these nice shapes with two double peaks. And the next epoch, one of them is bigger, the other one smaller, and the next epoch is the other way around. So the structure is definitely being kicked fairly badly. But it's also at the same time when S2 was flying by, and S2 is one of the strongest wind creators there. So S2 just beaming its wings this way can tear pieces out. It's fairly dynamical. So yes, it's quite possible that the structure we see is actually transient and happen something, but there is not enough data. So you have a second question.
Yeah, second question is, I'm trying to put this together, and so if you look as a function of radius, the mass in each component, so the black hole mass delta function, cold gas, hot gas, stellar material, it would be very nice if you could pull that together.
Yeah, I agree with you. We should definitely do
that. That would be very great.
Yeah, this plot, I don't have this one.
There is a question from Chet that has been waiting since a long time, and then we go to Angelo.
Can you guys hear me?
Yes.
Yes.
Yeah. So wonderful talk, Elena. So my mind kept going back to that old jet that you put on the slide, and it's oriented in a very interesting direction. And so and of course, this is of great interest to us in the EHT and NGHT because it speaks to the spin of the black hole and how that jet is generated. Does that give you any constraints on accretion, the fact that you may have to account for a jet? And does the age of that jet being old play into the stability question that Priya just asked and the generation of the accretion close in? In other words, I'm trying to fit that jet that may or may not exist in to the whole picture.
Let me show you whether this jet exists. I'll get a copy of this one and I remove the jet.
And also, is that jet real? There have been so many claims of jets around Sagittarius star. I never quite know what to believe.
No, there was many claims of the jets which are nearby, but that's a big thing. I've been there for. It's an old big thing. We don't really know how exactly it's oriented. So I think answering your question is, we know that some time ago Sagittarius were more active than right now. That's in itself an interesting question, but I think my current interest will mostly about what we see right now and what we can constrain about the knowledge of Sagittarius and star. And from this perspective, the jet at 1 parsec outside, and or maybe more, and extending to who knows how long, depends on the projection, would not actually help me much. So to study anything going on right now, so I see, for example, the small disk being kicked and changing its shape a little every year. So this thing to get to that size, been there for quite a long time ago. So it doesn't help me right now. Also, yes, my disk is also 10 to the 4 Schwarzschild radii, and it doesn't have to be aligned with the spin of the black hole. It has to be aligned with other things. So whether it gives you some information about the direction of the spin of the black hole, I think it kind of does. But again, it's hard to point what actually the direction of this jet.
Right. Well, I guess as a follow-on question, if the black hole is spinning, that would affect the emission given modes of accretion. So does that provide a constraint if you have to assume it's spinning or if it's not spinning? In other words,
still open to this 4 Schwarzschild radii is not that much, and we're not there yet. We'll definitely try. It will definitely influence variability, which coming from about 10 Schwarzschild radii. That's definitely influencing variability, and also variability feel how you feed the black hole. So, but we haven't done this experiment yet. It depends on like putting the spin in different directions and see what sort of consequences of variability has. But it does feel how it's a mechanism of its own field.
Thank you.
Andrew.
I had the same question as Jeff. Where can I read more about this jet feature?
The jet was pointed to me by Mark Morris, and the jet used to have a reference. And if I forgot it, I'll ask Mark Morris again.
Okay, yeah, I'd love to learn more about that. Is it only seen in X-ray, or are there any other?
I believe it's an X-ray. So you know, if I flash this, oh, darn, sorry. You can see that it's just like line in X-ray.
Okay.
People say that must be jet because
Yeah,
it's
I was
very
gonna say
straight.
it's seen.
Yeah, I agree.
But it's interesting.
Yes.
Yeah, so I have a question regarding to directionality of these streams at different scales and how much that would actually get connected to the basically galaxy properties versus the merger history versus the black hole properties. For instance, when you have clockwise or actually an anti-clockwise at different scales that may not be even matched together, how does it get driven by the properties of the of the typical scales nearby versus the further out or inside of the galaxy?
Properties of a typical disk. So
Whatever. I mean, that's the general question I have. Like
You mean how the properties of the stuff at larger distances and centra influence whatever's happening like very, very close to the black hole?
No, I mean, definitely there is a profile of the directionality of these different orbits, right? At a given time. Of course, there might be processing if you are long enough to actually to look at them, within some certain time. But even for now, any snapshot of them, you have some certain actually orbital types, right? At different scales that may or may not be connected to each other and to the stellar disk versus the black holes and so forth. So I wanted to know whether you have thoughts of it or is there any general picture that we can get. But for instance, when you have a very small scale, like fan dragging, you see that they actually the orbits of the gas that are basically orbiting around the black holes may be affected by the black hole itself. When you go further and further out, the directionality will be different. You have many orbits here at many different scales, and obviously they don't have the same orbital properties or the orientation. So in short, my question is there any connection to it that could be driven out of the entire things or?
So when you talk about the merger history and other things, you're talking about larger radii. So this one I have it here. I removed it from all of the slides except this one. Anyway, great, it's here. So this is thing which is the Keplerian fallout radius.
Yeah.
It's the radius at which gravity of the black hole starts dominating the motions of things. Outside this radius, it's no longer the black hole. It's a black hole plus tons of stars from the stellar cluster. So when you're talking about large radius, for you, what's important is just like there is a chunk of mass sitting there. Whatever is going like on the kiloparsec scale likely have very little influence on whatever is going to on the 10 parsec scale, and that has less influence what's going on the parsec scale. But what's going on the parsec scale, what's important here was that in my talk is that the mechanism of feeding is important for the black hole, but it's only right in this sort of area. When you go to kiloparsecs, anything else.
So can I have a quick follow-up on that? So actually, if I want to ask it differently, some people that work on the stellar orbits versus the spectroscopy, but they consider actually the age of these streams that could be driven by the metallicity of that stream, they could actually connect them. So you could imagine that there's a stream that because of some mergers or disruptions or stripping or whatever else, they have been inserted in your galaxy. And they have just like different orbits because they have different basically velocity of their stars. So in this case, although you may actually see them at different scales, at different orbits, they might be actually connected if you use the spectroscopy and stellar ages and stellar actually metallicity. So that kind of things, that's just something that I want to make a picture of it.
No,
if you have heard of it, if you have thought of it. And of course, you can just easily check them out in your simulation. If you have metallicity there.
Well, they're connected, the streams are connected to the galaxy, but it would be really hard to make your pieces of the stream and force them to go into this tiny region right here. They are at a much larger scale, so it's very disruptions events, but we're talking probably more than just kiloparsecs. We're talking about tens of hundreds of
KPCs.
tens of KPCs we're talking about. And depends for some streams, we're talking about hundreds of KPCs. So when something orbits at tens of KPC, it's really hard to make it lose orbital momentum, make it to the center of the galaxy. It's just a bunch of, from the point of view of this part of system, the gas system, it's just a bunch of bricks, heavy bricks flying through the gas, which doesn't do anything to them. They just like shooting through them.
See, Lena's treatment of detaching just the center is very valid. Basically, you don't need to worry about the gravitational influence of external structures. It's very justified.
So we have Lika, Ramesh, and then one last question on Zoom.
Okay, hi, yeah. Thank you for a great talk. This is definitely not my area of expertise, but I really love it. It's very interesting work in general. And I think I got a question on something that you said so much earlier when you were trying to test, like, have we seen this kind of cool stuff in simulations? And you were using the simulations of Wolf-Rayet stars for that quantified stellar system, right?
Mhm.
And you said, oh, you know, we can match observations in some sense. Yeah, but so I was wondering here, what kind of winds do you assume for the Wolf-Rayet winds? Because they can vary by orders of magnitude, right? So does it, if you just put in different winds, it doesn't match anymore?
I think it's I think there's a simple approach. They assume that each star sheds I forgot how much, but each star sheds the same. But the velocity of the winds is about 1,000 kilometers per second outside certain radius around the star. So just a simplified approach.
And do you think
it's doing this for thousands of years. Like in our case, it's doing it for 500,000 years. During that time, sure you might expect some little variation, but when we're trying to much orders of magnitude,
you don't think it will have a bigger effect if you say, okay, they lose 10 times more or 10 times less?
Like depends on which star, right? You can try to do it for each star and see whatever you see the difference.
Yeah.
So Sean did an experiment when he put the S2 into the picture and made S2 glow stars. And I think the conclusion was that Wolf-Rayet, 15 Wolf-Rayet still dominate this thing over the time. So yeah, it's you do the best you can. The simplest way. It's the simplest way you can.
Yeah.
And that gives you the result. That's amazing.
Yeah, I'm trying to understand the two-phase physics.
Yeah.
Right? I mean, you're simulating actually a complicated system, which has got hot gas.
Yes.
It's also got cold gas.
Yes.
And somehow you're kind of doing both of them simultaneously. So if I look at the hot phase itself, in these low m dot accretion flows, the density is so low that even though it's cooling, it doesn't really reduce the temperature.
Yeah.
It's being heated, it cools, everything is fine.
Exactly.
Except that the medium is intrinsically unstable, thermally unstable. So if I take a hot accretion flow and a little piece, I just increase its density temporarily by a large amount, suddenly it'll start cooling a lot. And once it gets into that phase, it won't come back.
Yeah.
It'll just cool, drop out of the hot phase, and I'll make a cold cloud, right? This is a feature of all these hot media, but you have to increase the density a lot. Great. Maybe that doesn't happen in these simulations because your m dot is very low. Maybe it does, I'm not sure. I can at least figure out, visualize how to go from hot to cold.
Yeah.
Okay. Meanwhile, you've got cold gas, which is being stripped out of the circumnuclear disk, maybe it's coming in, etc. And then I have to ask, how do I convert cold gas back to hot gas? Because I don't want a one-way street, right? I want to also have some balance between the two. One of the ways is friction, I guess. If this thing is falling in this hot medium, at the surface, there may be some friction, maybe I can evaporate some gas. That's probably being included in your simulations. But there's one other effect, which is often quite important, which is conduction. Anytime I've got a cold cloud sitting in a hot medium, there's a huge temperature gradient. So energy flows in through conduction from the hot medium to the cold medium. In fact, Karen is doing a lot of this with conventional thin disks. That's her work project, basically. That must be important. That's one way of evaporating gas because you're getting a new supply of energy. And I imagine that's not included in your Sean himself has done some work in the past, including conduction, but I'm sure it's too hard to include it in your simulations. I was just wondering, is that an important missing piece or does it not matter?
Well, thank you for the point. Yeah, I agree. I can't answer it on top of my head, but I think we should think about this and see how it goes. I agree.
This is why I didn't think it could be stable.
Yeah, exactly. Yeah, I think you need enough two-way communication to reach stable configuration, right? So I think, fortunately you do have through the friction, one mechanism to convert cold to hot. And if you can convince yourself that that dominates anyway, then you're okay. But including conduction is a horribly complicated problem. I don't think you can do it in the simulation.
So in short simulations before including the school structures, there was cooler phase appearing, but they were also disappearing as quickly as they were appearing.
Okay.
So that we definitely do lose cool phases when they appear. The question is, do we lose them as efficiently as we should?
Yeah, but also I'd like to know, how do you lose them? What is the reason for losing them once you're formed? Because I think the thermal instability says it's a one-way street. Once you've formed the cooling medium, it just keeps going to 0 degrees Kelvin until you stop it at 100 K or do some radiative transfer or whatever, then you just stop there. There's no reason for it to come back.
I agree. There is another process which is, it's the cool thing you live in a hot environment. In a hot environment, they do exchange temperatures, and the cool one will be heating up this way. So there are bunch of processes fighting over this.
Okay.
and who is going to win. So it's a complex question.
Yeah, we have a final question by Steve Wilner that I will read. So does the near-infrared rotating hotspot seen by the gravity interferometer fit into the picture you presented?
Say it again. Rotating hotspots seen by the gravity interferometers fit the same. They are much closer radii. So their statement is they are doing like this. This thing is angled. Whatever is happening at Q Schwarzschild radii doesn't have to be fitting to whatever is happening at 10 to the 4 Schwarzschild radii. So can be as disconnected as anything.
Okay. Yeah, very last question. Yeah.
Really quick question. So from this plot, I was confused because I thought the thin disk has to be aligned with the circumbinary test, but it seems like it's misaligned for some reason. It looks like a line to me when you show the code.
So there are bunch. You can see it here. So they are not aligned exactly. So this is observation. The simulation one is slightly off. Oh, see, I can see this one is visible here. So it's has the direction the observed one is a little bit like this. We don't include everything. There's still format. So it's not exactly in this direction, but the winds are also not in this direction. So sorry, wrong one. The directions of the winds in the this one, clockwise stellar system, you can see that direction is very offset. There's a bunch of directions which are continuously offset from each other. So whatever is forming can be anywhere around those, and doesn't have to exact much.
But does the angle change within this after forming?
We haven't run it for like another million years or something. So it's forming and it's lived there for 100.1 million years. And then it was the end of the simulations. So far just sitting there.
All right, let's thank Lena for being here.
Great work.
Yeah, very good.
Very nice. Reels of well. Yeah.
Priya, hi.
Hello, how are you?
Is it obvious?
Can't wait for you to get here.
I mean,
This
can
is
it
all
just
very
go
interesting
from
for what we are talking about.
here and
I found the paper, you don't have to.
Oh yeah, great. Thanks a lot.